Okay, today we're going to be looking at something called orbital filling order and electron configuration. So let's back up a bit. Here's what we know. 1. Atoms contain electrons. We're going to abbreviate this E negative. 2. Electrons are negatively charged. 3. Like charges repel. And so that presents atoms with a difficult proposition. And that is, where do they put their electrons so that they don't repel each other and existence as we know it comes to an end? Fortunately, we already know the answer to that question. Orbitals. And we've been spending some time identifying and describing the different orbitals that are available at different energy levels in an atom. So here's a quick recap. At the first energy level, we have one type of orbital available. It looks like this. Because this orbital is spherical, we're going to call it the S, and because it belongs in energy level 1, we'll call it the 1s. Here we are at the second energy level, what we call N is equal to 2. And here at the second energy level, we have an s orbital, and it looks like this. It's spherical, so we're going to call it the S, and it's in energy level 2, so we're going to call it the 2s, and notice how it's slightly bigger than our 1s. Also at the second energy level, we have a new type of orbital available, and that looks like this. It's the peanut-shaped orbital, or we'll abbreviate it to P, and there's actually 3 of them because there's 3 different ways to point this. They are shaped like this so that they can all occupy the same space but don't interfere with each other. And individually they look like this. We'll call this one, since it's on the x-axis, the 2px. This one's the 2py, and this one's the 2pz. They're all identical. The only thing that's different is the way they're pointing. And there are 3 of them. At the third energy level, we have our S's and P's, and they look like this. This is our 3s, and here is our 3px, our 3py, and our 3pz. We're not worried about which one of these particular, we just know that there are 3 total. And also at the third energy level, we have a new type of orbital, and it looks like this. These are our d orbitals, and they are shaped kind of like a double peanut, I guess, if you squint. And what we're mostly concerned with is that there are 5 of these, and they're all identical. These are what we're going to call the 3d orbitals, and there are 1, 2, 3, 4, 5. We're not going to worry about which orientation we're talking about either, just that there are. And lastly, at the fourth energy level, we are at n equals 4, and our orbitals that are available here are, we have an S-shaped orbital, our 4s. We have 3 identical p orbitals at energy level 4, and we have our 5 identical d orbitals at energy level 4, and we're going to call these the 4ds. But at the fourth energy level, we have a new shape of orbital, and that looks like this. These are called f orbitals. We'll call them 4f's because they're at energy level 4, and there are 7 And let's remember that in every single case, each of these orbitals can hold only 2 electrons. And only if one electron is spinning in the up direction and the other is spinning in the down direction can one orbital hold 2 electrons without them repelling. So how does this work? So what we're going to be looking at is what's called filling order, and we are going to follow 3 rules of filling order. And our first rule, the Aufbau principle, says that electrons will occupy the lowest energy level orbital that will receive it. So in other words, the lowest available orbital must fill first. Remember that we said that energy levels are like floors in a building. So this is saying that we have to fill the lowest floors first. Let's take a look at our next rule. This is called Hund's rule, and this one says that electrons will occupy all empty orbitals in a subshell with single electrons having parallel spins before entering half-filled orbitals. All this means is that we have to fill the empty ones first. And we have one more rule. This one is called the Pauli exclusion principle, and it says that no 2 electrons within an atom may have an identical set of all 4 quantum numbers. This just means that electrons can't occupy the exact same space. And that's all this says. So now that we have these 3 rules, let's see how this works. So here we have a diagram that shows us all the available orbitals at every energy level. And they're just shown as a square. And it's not indicating what their shape is because it doesn't matter. What we see on the left side is this axis that shows increasing energy, and what that tells us is that all of the orbitals that are here at the lower end, at the bottom end, are lower in energy, and that as we go up they increase. What that means is that 1s is lower in energy than 2s, and that in the second energy level itself the 2p's are slightly higher in energy than the 2s. And so we're going to fill these in order. And pay attention, because the ones that are perfectly level with each other are going to be orbitals that have the exact same energy. So let's try one. Alright, here we see helium. It has an atomic number of 2. And what this means is that it has a total of 2 electrons we have to keep in mind as we're filling. So I'm going to zoom in a bit. So we're going to follow the Aufbau principle, which says you have to fill the lowest energy orbitals first. We're going to follow the Hund rule, which says that you have to keep them separate for as long as you can. They have to occupy empty orbitals first before they'll share one. And finally, we want to keep in mind the Pauli exclusion principle, which says that no 2 electrons can have the same set of quantum numbers. So we have 2 electrons in helium, and here's how we're going to do this. Aufbau says you got to fill the lowest energy orbital first. That's 1s. We're going to put 1 electron in this orbital because it can hold 2 as long as they're spinning in the opposite direction. Now, Aufbau says you got to fill the lowest ones first. Well, this one isn't full, and you can share them as long as they're spinning in opposite directions. So we're going to say that this atom of helium keeps its 2 electrons, the only 2 that it has, in the 1s orbital. And so we're going to indicate that there are 2 electrons in the 1s, and we read this 1s2. Let's do another one. So let's do our old buddy carbon, and it's got an atomic number of 6, and that means that we have 6 electrons that we have to put in these orbitals in such a way that they fulfill all of these 3 laws. So let's zoom in a bit. We have 6 electrons. So we're going to fill the 1s orbital first because it is lowest, and they can share an orbital as long as they're spinning in opposite directions. And so we have 4 left. Well, there's no more room at the first energy level. So Aufbau says now we have to go to the next highest. And there are 6. We used 2 of them in our 1s. So now we're going to go to the 2s, and we're going to put 2 electrons there. And remember that 2s is lower in energy. It's the next lowest available orbital. So we're going to fill that one first. So of our 6 electrons that we had, we put 2 in the 1s and 2 in the 2s, but we still have 2 left. And so they're going to go in the 2p, but here is where our Hund's rule is going to come into play. Of our 2 electrons, we're going to put 1 here in any one of the 2p orbitals. It doesn't really matter which. And where does the second one go? The last electron that we're going to fill here? It doesn't matter where as long as it doesn't go here, because that violates Hund's rule. They have to remain separate and fill empty orbitals first. And it doesn't matter where they go. And so now we're going to write this as having an electron configuration of 1s2, meaning it has 2 electrons in the 1s. 2s2, meaning it has 2 electrons in the 2s, and 2p2, meaning that it has 2 electrons in the 2p. Let's do one more, and then I think we got the hang of it. Alright, last one we're going to do today, and this is chlorine. And according to its atomic number, it has 17 electrons that we have to put in all of these orbitals to fulfill the Aufbau rule and the Hund's rule and Pauli exclusion to make sure that they don't interfere with each other. So let's zoom in a bit. Oops. So we have 17 electrons that we're going to stash. We're going to start with the lowest available energy orbital, which is 1s. There's an up spin and a down spin. We have 15 left, so they're going to go next to the 2s. There's an up spin and a down spin. We've got 13 left, so we're going to go next to the 2p. And we're going to fill each of these individually for as long as we can. But now we've got 10 left we have to fill, so we can't just jump to the next energy level. We got to fill this one first. So here are the next 3, and that leaves us with 7 electrons that we still have to stash, because there's 2 here in the 1s, there's 2 here in the 2s, and there's 6 altogether in all of the 2p's. Well, we have 17, so we've got 7 left that we've got to stash. So we're going to put them here in the 3s, and that fills the 3s. And so now, with the remaining 5, we're going to keep them separate for as long as we can. But we still have 2 left, and so we'll put those in the remaining 3p's. So our electron configuration for chlorine is 1s2, 2s2, 2p6 because there are 6 electrons in the 2p's, 3s2 because there are 2 electrons in the 3s's, and altogether there are 5 electrons in the 3p's, so we'll say 3p5. And the last thing that we'll say about this is that when we write out this in this format, this is what we're going to call the electron configuration notation, because it doesn't really concern itself with individual orbitals. But this setup, where we're actually showing the individual orbitals, we'll call this orbital notation, because it actually shows the individual orbitals. All right, I'd like you guys to take that for a spin. All right, and we'll keep it simple like this for a little while. All right, see you on the next one.